Okay. So I think we should be good. My chat's not, can you guys still type in the chat? Because I haven't seen anything in a little bit. Okay. All right. Sounds good. All right. 7-2. Let's go through 7-2. I think we should be able to finish it kind of quickly. So that would be nice to do today, right? Kind of a good week for that. So 7-1, we talked about solving systems of equations, right? And I really wanted to talk about linear equations. But 7.2, we're going to talk specifically about linear equations and an additional method that works well for solving linear equations. It doesn't always work well for solving systems of equations. Okay, so pull up our notes here. You could technically use the elimination method for any system of equation, but really linear equations is where it makes the most sense. So really, I think to do this, we want to just do some examples. You'll see up here there's some steps to how to do the method of elimination, but we want to first obtain coefficients for x or y that differ only in a sign by multiplying all the terms of one or both equations by suitably chosen constants. Okay, sounds very formal. And then we want to add the equations to eliminate one variable, solving the resulting equation. Back substitute the value into one of the original equations, and then check your solution in both of the equations. Okay, so let's do some examples. And hopefully this is review for you guys, so that's always nice. There's not nearly as many homework problems in 7-2. It's 1 through 15 odd and 17 through 20, which I have on my sheet. So we should be pretty good. All right, so let's start with number 2 is really easy peasy. So maybe let's start with number 4. Okay, so number 4, they actually give you the graph, so you already have a preview of what you know the solution is, because one possible solution to solving any system of equations is to graph it and to find the points of intersection, right? So this is a tiny little graph. I can't even put my finger where they intersect on there, but we know it's going to be a positive x and positive y, maybe about, I'm guessing 4, something like that, just based off of my graph. You guys have younger eyes, so you might be able to see that. So in the method of elimination, again, this is one of many tools that you can use to solve systems of equations. We're trying to find what x and y makes both equations true. Okay. For elimination, what we're going to do is we're going to try to either find an x or a y. We're going to try to find or make an x or a y that matches up with a value in the other equation, so that when we add them together, then we will eliminate one of the variables. Okay, so in number 4, we have 2x minus y equals 3, and we have 4x plus 3y equals 21. Okay, so what I want to do is I want to multiply by a constant one of these equations in order to make it so that when I add the equations together, something cancels out. So for me, when I look at these equations, I think the easiest thing to do would be to multiply my top equation by 3. Okay, so I want to multiply this side of my equation by 3 and this side of my equation by 3. And we're allowed to do that because we're doing the same thing to both sides of the equation, right? We're just making basically a multiple of the equation. The reason I want to do that has to do with right here, I have a positive 3y. So if I can turn this into a negative 3y, when I add my two equations together, I eliminate y altogether. So that's how I picked to multiply by 3. I looked for my terms and I said, oh, well, this is positive 3y. This is a negative y. If I just multiply by 3, I get negative 3y, and then I cancel out. Okay, so then what we do, that's step 1, is we multiply by some constant. So our new first equation becomes 6x minus 3y equals 9. Okay, and our second equation stays the same, right? It's still 4x plus 3y equals 21. But by multiplying by that constant of 3, right, I have a positive 3y and a negative 3y. So if I add my two equations together, I get 6x plus 4x is 10x, right? Negative 3y plus positive 3y is no y, 0y, right? And 21 plus 9 is 30. And I get x equals 3. I was pretty close with my squinty eyes on there, right? So I've added the equations together to eliminate one variable, and I've solved the resulting equation. So now I know x equals 3. Now I need to figure out, well, when x equals 3, what does y equal, right? So I do that by back substituting into either of my original equations. So I can pick one of the two. I'm going to go ahead and pick my first one again, this one up here. And I'm going to say it's 2x minus y equals 3. I'm going to plug in x equals 3. So 2 times 3 minus y equals 3. And so this is basically, I'm taking a little shortcut here. Subtract 6 from both sides. So I get minus y equals minus 3, or y equals 3. So the ordered pair solution to my equation is 3, 3, which looks like on my graph. I was thinking 4, 4, but that's pretty close, right? If I made my graph a little bigger. If I used a graphing tool, I could actually see exactly where it's at. And then, of course, the last step is to check. Well, yes, check your solution in both equations. And again, this could be formal. You could write out 2 times 3 minus 3. Does that equal 3? Yes, that does. 4 times 3, which is 12, plus 3 times 3, which is 9. Does 12 plus 9 equal 21? Yes, it does. So that's kind of like a, sometimes it needs to be formal. Sometimes it's just like kind of a gut check as to how to do that. Has everybody seen this before? Is this like easy peasy? Mm-hmm. Okay. It is pretty easy, Jennifer. Okay. Really quickly, since we have it up here, I'm not going to spend super long on this, but let's look at 5 and 6 since they have, spoiler alert, they give you the graph, so you kind of know what's going to happen here. There we go. So if you look at number 5, and we talked about this on Monday also, if you look at number 5, they already show you the graph of number 5. And so just based off of this graph, what's your guess as to what are the solutions to this system of equations? We have x minus y equals 2 and minus 2x plus 2y equals 5. And this gigantic window that we have here. So based on looking at this, these look like two parallel lines, right? They appear to have the same slope. Yes. They're going to have the same slope, right? Yep, there is no solution. That's right, Jennifer. It looks like these are two parallel lines. There's no solution. The reason that I threw this example up here is sometimes you don't start with a graph. Sometimes you start with elimination. So if we had started with elimination, what would this look like when we were doing our work? Okay, so we have these equations. We have x minus y equals 2. So yes, Jennifer, I agree. Based off the graph and looking at our equations that have the same slope, we could say that there is no solution, right? But if you didn't have the graph first and you were just diving right into elimination, what would this look like when you're solving your equation? So if I was doing the elimination method, I didn't see my picture here. okay? And I wanted to eliminate one variable. This is pretty easy. I'm going to multiply the top by 2, right? Because if I have 2 times x, I'll get positive 2x plus negative 2x, and that's going to eliminate x for me. And that's really not the right syntax. I should really write it like this. We're multiplying both sides by 2. Okay, so if I basically transform my top equation by multiplying by 2, I get 2x minus 2y equals 4. Okay, my second equation stays the same, minus 2x plus 2y equals 5. So then when I go to add my two equations together, I have 2x plus negative 2x, so that's 0, right? And then I have negative 2y plus positive 2y, which is also 0. But I have 4 plus 5, which is 9. So you can see when you do the elimination method and you end up with a false statement, like 0 equals 9, then that's a clue that you have no, yeah, somehow we've proved that 0 equals 9. We're math geniuses. So that's your clue when you're doing the elimination method that, hey, something's not right here. I need to look at this a little further. And actually, it's actually the clue that, hey, these two systems of equations have no solution. Multiply 0 by 0 and it's a solution. Yes, that is not a allowable mathematical principle to multiply both sides of your equation by 0. Then everything would be a solution, right? I like the way you're thinking though, Aiden. Oh, okay, that's a box. All right, so really quickly then, number 6, surprise, surprise. Number 6 is our case where we have infinitely many solutions, right? We have both lines are lying on top of each other. At least that's what it looks like in their picture. So when we solve a system of linear equations using the elimination method and we have infinitely many solutions, what does that look like? Then we get Aiden's solution there. We get good old 0 equals 0. So let's just show real fast. We have 3x minus 2y equals 5. Okay. And we have negative 6x plus 4y equals negative 10. So I might as well eliminate x because that's nice and easy. All I need to do to basically transform 3x into 6x is to multiply everything by 2. Right? So my top equation becomes 6x minus 4y equals 10. My second equation remains the same. This should feel vaguely familiar. So then when I add them together, right, 6x plus negative 6x is 0. 4y plus negative 4y equals 0. And 10 plus negative 10 equals 0. So now, Aiden, we do have 0 equals 0. And that's our tip off that, oh, this is infinitely many solutions, because that is a true statement. Now, there are some funny ways that you could kind of end up with that sometimes. So you always want to double check, go back and check either graphically or by putting some different solutions in that you didn't kind of mess up and end up with 0 equals 0. But again, that's kind of a tip off that there's infinitely many solutions. Okay, 2 more examples, and then I think we should be on our way. I wanted to do number 14 because it's a little bit more complex of a problem. Trying to zoom in. That's what I should have done on my graphs before. So much easier to see. Okay, number 14, we have 3u plus 11v equals 4, and negative 2u minus 5v equals 9. And we want to solve this system of, well, linear equations by elimination. Okay, so these last few problems here get a little bit more tricky because in our first few examples, we just had to transform basically one equation. We basically had to choose one equation, multiply it by a constant, and voila, we were able to add. What you'll notice here is that we have, for our coefficients of u, we have 3 and negative 2. So unless I plan on multiplying by fractions, which you could do, then we need to transform both the top and the bottom. The same with our v, right? The coefficients of v are 11 and negative 5. There's no easy constant that's a whole number that I can multiply by both to make them the same. So what I'm going to do is I'm actually going to multiply both the top and the bottom equation by a constant in order to cancel out. So in my mind, what I'm thinking is that probably the easiest is if I can transform 3u and 2u into positive and negative 6u. It's supposed to be a u here. 6u. Okay, so I can do that if I multiply the top equation by a constant of 2, right? So the top equation is going to be 2 times 3u plus 11v equals 2 times 4. So if I simplify my top equation, it becomes 6u plus 22v equals 8. Okay. My second equation, in order to have a coefficient of 6, right, I need to multiply by 3. So I'm going to do 3 times negative 2u minus 5v equals 3 times 9. So if I simplify, I get negative 6u minus 15v equals 27. So now I'm going to add my two equations together. And again, to just kind of speed things up here, I'm going to erase this so we can, there we go. All right, so these are my two transformed equations, right? I've multiplied both of my equations by a constant. And now if I add them together, I get 6u plus negative 6u, that's 0. I get 22v plus negative 15v, and that is 7v. And then I have 27 plus 8, which is 35. Divide both sides by 7, and I get v equals 5. Always good when you end up with a nice whole number in these problems, right? So now I've solved for v, so now I want to go back and solve for u. So that's back substituting is what your book calls it, right? When I do these problems, what I like to do is I like to go back to one of the original problems, just in case I messed up somewhere with my numbers. I just like to go back to the original. So if I pick the second one, it doesn't really matter. I have negative 2u minus 5v, 5 times v, and v is 5, right? Equals 9. So this is negative 2u minus 25 equals 9. Add 25 to both sides, so I get negative 2u equals 34. Or u equals negative 17. So my solution is negative 17, 5. So then my choices to check my work, right, are to substitute negative 17.5 into both of these and check and make sure that it works. I could also graph the two and make sure that that's my intersection point. Okay. Not too bad stuff, right? All right, last example, unless anybody has any other questions. Oh, that's not our notes. And these are actually in your homework. 17 through 20 is in your homework. So we'll just give you a little head start on that. It says in exercises 17 through 20, match the system of linear equations with its graph, state the number of solutions, then state whether the system is consistent or inconsistent, which we haven't talked about yet. And the graphs are labeled A, B, C, and D. Okay, so let me tell you what the definition of a consistent equation is. A consistent equation is one that has at least one solution. So I can tell you just by, so consistent means it has at least one solution. An inconsistent equation has, an inconsistent system has no solutions. Okay, so just by looking at my graphs here, I can tell you that A would be a consistent equation, or consistent system of equations, excuse me, because there's definitely at least one solution. There's infinitely many solutions, right? B also appears to be a consistent system because there is one solution right here. Okay, if I can draw a C. C also appears to be a consistent equation, or a system of equations. I want to say equation. Consistent system, because there's one solution. And D over here appears to be two parallel lines with no solution, so this would be inconsistent because there is not at least one solution. Okay. Everything else should appear to be pretty easy. So if you just, we're not asking you to, or I'm not asking you to solve in any of these, you're just matching the system of linear equations with its graph. So you can look at the equations. You could also put it in a graphing tool and see what you get. I don't know if you guys want to see any more examples or you feel like, okay, I got it. Can anyone, just by looking at these, identify which one do you think is going to be our no solution case? Yeah, awesome, Sarah. Exactly. We have 7x, yeah, number 20, 20 and D, right? So when you look here, they have your coefficient terms already lined up, right? 7x plus negative 7x is 0. Negative 6y plus positive 6y is 0. So this is 0. And then negative 6 plus negative 4 is negative 10. Right? So we are looking at 0 equals negative 10, which would be a feat of mathematics if we could get that to work, right? So that pretty much tells us that that is going to be inconsistent. There's no solution, and that's our graph is going to be D. Okay. Yeah. So then the other ones will just match up from there. Okay. I really didn't have any more examples today. It's pretty much as simple as that. On Monday, we're going to talk about multivariable linear equations. So that's not only there, these are still linear equations, but we have X, Y, and Z. So we have 3 terms. We can even have 4 terms. There are a few ways that we can solve these types of multivariable linear equations, but we'll kind of dive into that on Monday. So, and that's all I have for you guys today. Keep that link that I sent you. That's what we'll use from now on. Hopefully that'll work for us. You can stay on if you have any questions. If not, I hope you have an awesome day. Thanks, guys. Thanks. Have a great day.